And the next talk is on black box separations of quantum digital signatures from pseudorandom states by Andrea Coladangelo, Sachi Mutrecha, and Sachi is going to give the talk.
Hi everyone, I'm Sachi, and I'm going to be talking about black box separations of quantum digital signature schemes from pseudorandom states, and this is joint work with Andrea Coladangelo. So this work is about relationships between primitives in quantum cryptography. So a good way to motivate that is talking about Impagliozzo's 5 worlds. So these are 5 possible resolutions to the P and P question, ranging all the way from Algorithmica, a world where P equals NP, all the way to Cryptomania, where not only is P not equal to NP, but public key encryption exists. So if you're a cryptographer, then ideally we want to be living in mini-crypt or Cryptomania. And the reason is that in these 2 worlds, a primitive called one-way functions exists. And this is really the minimal primitive in classical cryptography, meaning if you hope to do any type of basic, if you hope to implement any type of basic functionalities in classical cryptography, you need at least one-way functions. So switching to the quantum world, we can ask the question, are one-way functions necessary in the quantum world as well? And if not, then what are the minimal assumptions that are required to build quantum cryptography? And inspired by this question, the class microcrypt was coined by Tomoyuki Morime, and this is a set of primitives that are potentially weaker than one-way functions. And these are quantum primitives, so their security is formulated in terms of the hardness of an inherently quantum problem. And although they're weaker than one-way functions, this class contains primitives like pseudorandom states, one-way state generators, and many more primitives. So this talk today will be focusing on pseudorandom states and its relationships with other primitives in quantum cryptography. So I'll start by defining intuitively what a pseudorandom state is. So you can think of a pseudorandom state as a quantum analog of a pseudorandom generator from classical cryptography. And intuitively, it's just, these are computational approximations to the Haar measure. And I like to think of the Haar measure, so we can think of the set of all possible n-qubit states as a sphere of high dimension. And a Haar random state is just a dot on the sphere. That's how I like to think of it. So, and pseudorandom states are just states that look like a Haar random state. So more formally, it's just a pseudorandom state is just a pair of efficient quantum polytime algorithms. There's a gen key algorithm, which takes in some security parameter, outputs a key k. And then given a key k, there's a gen state algorithm, which outputs an n-qubit state. And this is our PRS state. And for all, the security guarantees the following. For all polynomials T and for all polytime algorithms D, which we call distinguishers, T copies of a pseudorandom state are indistinguishable from T copies of a Haar random state. And the notion of copies matters here because quantum states are not clonable. So what is known about pseudorandom states? This notion was introduced in 2018 by Ji Liu and Song, and they showed that pseudorandom states can be constructed in a black box way from quantum secure one-way functions. And in 2021, William Kretschmer showed that one-way functions cannot be constructed from pseudorandom functions in a black box way. So in other words, he showed that there exists an oracle relative to which pseudorandom states exist, but quantum secure one-way functions don't exist. So this is why pseudorandom states are in microcrypt, because this means they're potentially weaker than one-way functions. But turns out we can do a lot of interesting quantum cryptography from them, and the question that this work contributes towards is, where do pseudorandom states fit in the complexity landscape? And in particular, we explore the relationship between pseudorandom states and a primitive called quantum digital signatures. So I'll start by recapping what a classical digital signature scheme is. So it's just, if let's say I'm Alice and I want to send a message to Bob, a digital signature scheme allows me to authenticate my message in a way that Bob can verify it with a public key and see if there's any tampering or man-in-the-middle attacks. So more formally, a digital signature scheme is just a tuple of algorithms. There's a secret key generation algorithm which outputs the secret key. This key is used to sign messages. There's a public key generation algorithm which is used for verification of signed messages. And there's a signing algorithm, which takes in a message M, signs it with the secret key. And there's a verification algorithm, which takes in a message and a candidate signature, verifies it with the public key, and then either accepts or rejects. And security is formulated in terms of an unforgeability game between a challenger and an adversary. And the game is the following. The adversary gets a copy of the public key, and then the adversary is allowed to query the signing oracle on messages of its choice, and the guarantee is that it's going to get correct signatures on all the messages it queries. And after that, in the challenge phase, it has to come up with a fresh message and a correct signature on that message. And if it's able to do that, it wins the game. And we say that a DS scheme is secure if no computationally bounded adversary can win this game with probability that's more than negligible. So there's different notions of security that we're going to consider. The first one is a one-time secure DS scheme. And a one-time secure DS scheme is exactly the same game, but the adversary is only allowed to query the signing oracle once before it has to come up with a message and a valid signature. And a many-time secure DS scheme is one where the adversary is allowed to query on polynomially many messages of its own choice. It gets valid signatures, and then it enters the challenge phase. So classical digital signatures imply one-way functions, so clearly they cannot be in microcrypt. So we introduce, or this has been introduced in prior work, but we focus on a quantum notion of DS schemes, which we call quantum public key digital signatures. And this is more or less similar to the notion of a classical DS scheme, but all the algorithms are QPT. And furthermore, the PKGen algorithm outputs a public key that's a quantum state, a pure quantum state, instead of a classical public key. These are the main differences. And prior work shows that given a PRS state, there is a black box construction from a PRS state to a one-time secure QDS scheme with a quantum public key. So one-time secure just means, like I said, the adversary is only allowed to query the signing oracle once before entering the challenge phase. So the question of whether there exists a multi-time secure QDS scheme with quantum public keys from PRS states was left open. And so in this work, we resolved this question. In the negative, in particular, we proved that there exists a quantum oracle relative to which PRS schemes don't exist relative to O, and PRS schemes exist relative to O, and no multi-time secure QDS scheme exists relative to O. So as a corollary, our result says that there does not exist a fully black box construction of multi-time secure QDS schemes from pseudorandom states. So that's the result. And I'll start by describing what the oracle is. So it's a quantum oracle, and it's a pair of oracles. So we have a classical oracle for a fixed X complete problem, which we call Q. And then we have a quantum oracle U. And I like to think of this oracle as a set of sets. So U is a collection of random unitaries, U sub L, for all L. And each U sub L is an indexed list of 2 to the L random unitaries acting on L qubits. So it's a set of ULs where each UL is a set of 2 to the L random unitaries. That's the quantum oracle. And the easy part of this result is proving that pseudorandom states exist relative to this oracle. So I'll focus more on on constructing an adversary for any QDS scheme, a multi-time secure QDS scheme relative to this oracle. So when we first look at this oracle, we have a classical oracle for an X complete problem, and to win the security game of a multi-time secure QDS scheme, we have to come up with a valid signature on a message of our own choice, freshly sampled. So kind of the first idea would be to use Q to perform some sort of brute force over secret keys to find a secret key such that when you sign a message of your own, sign a freshly sampled message with that secret key, that signature should pass verification with the public key that's generated from the original secret key, which we call SK star. So there's this is the right idea, but there's some challenges we have to overcome. And the first challenge is that when Q is performing any type of brute force search, it's going to run the verification algorithm many, many times and see, which secret keys are good versus not. So, however, every single algorithm, all the evaluation algorithms in the QDS scheme, they're querying this quantum oracle U, which doesn't have a succinct description. And furthermore, Q is sampled independently of U, so there's no way to hard code the description of this giant quantum oracle into Q. So how can we use Q to perform a brute force search? And we do this by kind of proving that the quantum oracle is useless. A better way of saying is that we can simulate queries to the Harnum oracle U by making a fresh query to a fresh Harnum unitary U prime. And we can do this because of the properties of the strong concentration of the Haar measure. So a bit more formally, if we have a quantum circuit C that makes polynomially many queries to a Harnum unitary, then with high probability over sampling two such Harnum unitaries U and U prime for any standard basis input X, the probability that C on input X when it's querying U outputs 1 is very close to the probability that C on input X outputs 1 when it's querying U prime instead. So Q can still perform the brute force search, but every time the QDS algorithm is querying U, it just replaces it with a query to U prime. So in this way, it can perform brute force search without making any queries to U. And furthermore, this concentration is so strong that it can support a union bound over all possible states. So we can do union bounds over all possible secret keys, and the number of secret keys are classical. So this bound still holds. So in our case, the circuit C that we feed into the classical oracle Q is just it's just this verification circuit that's querying Q. It's not querying U, and then the pkgen, and then M, and then we have to find a good secret key. And there's some more nuances here. For example, the public key is a quantum state, so we cannot run brute force with the public key because we only have polynomially many copies of the public key. So in order to get around that, we instead feed a description of pkgen to Q instead. So, and then a public key is just the circuit pkgen run with a candidate secret key. So now Q can perform brute force search over secret keys and get a good signing secret key. So there's a lot of technical details I'm skipping over, but you should check the full version for that. So in summary, A makes polynomially many queries to the signing oracle. The attack is the following. The adversary makes the queries. It obtains message signature pairs. Then we run a clever brute force attack using Q, and we identify a shrinking set of candidate secret keys. And then Q will sample a secret key from this candidate set of secret keys, and then return it to A, and A will sign a fresh message with the secret key. And I'm going to skip over the details. Okay, so now I'll talk about pseudorandom states existing relative to O. So in this paper, we prove that pseudorandom unitaries exist relative to O, which implies that pseudorandom states exist relative to O. And the construction is simple. It's just if you have input key K, just sample a unitary from the set U sub length of K, and then that's a Harnum unitary, so it's definitely pseudorandom as well, and that implies pseudorandom states. And that's it. Thank you.
We have time for a quick question.
So I was wondering, what's the point of considering digital signatures with a quantum public key? I know that you're showing impossibility, but still.
What do you mean, what's the point?
I mean, quantum public key, in what way is it that signature, right? The public key, it's changing, right? You know, once you check with it, either a good or a bad signature is gone, right?
Yeah, that's definitely like,
Even a one-time signature scheme doesn't make sense
yeah,
much.
so the way I like to think of it is you can imagine like there's a quantum Amazon where like you have like many copies of the quantum public key, and you're right, every time you run verification, the quantum public key is destroyed. But in the security game, the adversary is allowed to get up to polynomially many copies of the public key, so it can perform up to polynomially many verifications. So,
Okay, right, okay. But I guess you're showing a negative result, so it's even that is, I guess, is impossible, a black box way.
yeah.
Okay.
All right, let's thank Andrea again.